probably start to get a little carpal tunnel developing out of that and not particularly happy with it. Okay? But that's just writing stuff down. It's not that bad. If you know how to enter that into your calculator, okay, you're still only hitting 2 buttons, but the more times you have to move around that screen, the more likely, instead of doing times 4, you're going to do times 1, times 6, okay, times 5. What does that mean happens to your calculation? It's wrong. You need to do it all over again. So if you do it wrong enough times, you end up cycling through it a whole bunch of times and keep getting the answer wrong. You get even sick or even more sick and tired of doing the calculation. So it might be nice if we came up with a way to shorthand that calculation. What's our shorthand? Okay. We can say that this is 4 to the 6th power. Right? Just some of the kind of basic math ideas that hopefully you guys have already seen. So we will see exponents. It's just breaking that down and repeating. Is it 6 times? Okay. I just saw some people laughing, and I thought maybe because I didn't do that right. Well, there. Except now the 4 doesn't show up. Even better. Okay. So what we've got now is the exponents. So some common terms that come along with this, you can run into squared and cubed, which are ultimately coming out of geometry. Okay. Cubed means we're holding it to the 3rd power. Why cubed? If we measure the area of a cube, it would be the length, that's my fault, not yours, width and height. In this case, it would be 3 times 3 times 3 for each of those cubes. So hence cube. Square, we're holding it to the 2nd power because the area in a square is length times width. That's where those terms are coming from. Okay, trying to keep it relatively straightforward and simple there. Okay. Next thing that we'll encounter is kind of putting it all together. We'll do powers of 10. Okay. And when we move into chapter 2, which we will do here in just a little bit, there's that stupid King Henry slaughters things. What is it? Oh, he actually died. It was pretty close. King Henry died by drinking chocolate milk, or whatever that stupid saying is. And, oh, you just shift the decimal. It is a load of complete and utter crap. I cannot believe they teach you that. What they're teaching you to do is to memorize some nonsense string of things, to then do a nonsense string of shifting decimal points, which is completely arbitrary and nonsensical. Don't do that. Okay? That said, if you do it correctly, there's nothing I can do about it except say don't do that. Okay? Where it's going to become a problem is when you do it incorrectly, all you're going to get out of me is neener, 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 you did it wrong because you followed that stupid method. Okay? It's not just a question of shifting decimal points. We have to understand the meaning behind what those things are saying. Okay? So those of you who don't know King Henry and all that, you're better off without it. Okay? Those of you that do, forget it. Okay? And it is tied back to these powers of 10. Okay? So if we wanted to scale something up, say 100, okay? Well, we could simplify that, simplify that into a power of 10 notation. Okay? That is the same, where's my number, as taking 10 times 10. Okay? Also known as 10 squared. Okay? So I could write out 100 as 1 times 10 squared. You'd all be like, well, that was a complete waste of time. You did more pen strokes to write 1 times 10 squared than you did by writing 100. And you're right, I did. Okay? But when we scale up to, say, what is the other number? 1,000,000? Okay? The number of pen strokes drops significantly. Okay. If we push this even further, 1,000,000 is tiny in comparison to the numbers that we will work with later in the semester. The numbers we will work with later in the semester on the order of 10 to the 26th. That's a hell of a lot of zeros to have to string after every single number. Okay. So we want to take advantage of these powers of 10, realize what they're meaning. Okay. So it's a combination of our powers of 10 feature, which is useful for our metric system, and our exponent abilities. Okay? You'll notice that we could say 10 to the positive 26, in which case we're looking at a really, really big number. What if we put a negative in there? Then we're looking at a really negative number. Is that where I'm talking about putting a negative? No. Where are we talking about putting a negative? Negative 26. It is a really, really small number. Is it less than 0? No. It's still a positive number. It's just really, really close to 0. Okay? And again, it's kind of an idea of where you're shifting the decimal value. Okay? Last thing we'll kind of do is put it all together and we'll run up with this idea of scientific notation, which is ultimately just lazy. Okay? This comes back to our powers of 10. We don't want to write out, say, what is that number? 406,300,000 meters as the distance between the Earth and the Moon. Okay? Or that other really, really tiny number that I'm not even going to pretend to say because I can't figure it out. So what we'll do is convert it into a scientific notation so that it's easier to kind of interpret it. We don't have to see all those zeros following at the end. Okay? We can just kind of group those together as a power of 10. Okay? So what we'll do is convert those numbers into the format shown below. This is now our scientific notation. Okay? Number in our ones place, followed by a decimal point, followed by all of our significant digits. Okay? This can become very helpful if we wanted to, say, include the zeros as significant digits. If we look at our distance between the Earth and the Moon, to convert that into scientific notation, it would become 4.063, and if I want my zeros to be significant digits, 0, 0, 1, 2, 3, times 10 to the, right, we have to figure out how far we've shifted our decimal. We went 1, 2, 3, 4, 5, 6, 7, 8 locations. Okay. Are we describing a really big number or a really small number? A really big number, which means the sign in front of my 8 should be positive. And I now have my number. Okay. With all of those zeros being significant digits. But according to our significant digit rule, how many of those zeros should be significant? 4 is significant, 6 is significant, 3 is significant. Is this 0 significant?
Yes.
Why?
Because the left is
So you're giving me a left, and I heard a right float in there, and I would argue both of those analyses are wrong. What are you suggesting? It's still going to be the wrong idea. In the middle of two significant digits is relevant only when we're looking for decimal points. It's all about a decimal point. Is there a decimal point there? No. So what is the rule without a decimal point? It must be to the left and to the right. Now we can evaluate it's between two, which then means the 0 is significant. What about those other zeros? Why not? Without the decimal point, I must be controlled on both sides. To the left, I am. To the other side, I'm not. Which would mean the number I would need to write, if I'm going to interpret it exactly as it is written, would be 4.063 times 10 to the 8th. And I've now covered my bases. Okay. That gets us 4 significant digits. How can I write this where it is now 5 significant digits? Add a 0 where? End of what? 4.0630 times 10 to the, it's still 8th. The 8th is based on where your decimal point is. We haven't changed the location of the decimal point. Okay. So let's take a moment here. I did this in the wrong order. So we just talked for roughly 5 minutes about scientific notation, right? Everybody okay with that? Okay. Flash, freeze, whatever you want to do, remove that from your memory. Whatever you got to do here. Ta-da, it's all gone. You have no idea what we're talking about. Scientific notation, report the number shown to 5 sig figs. (406300,000 meters to 5 sig figs. I all frantically wrote stuff down, so now I'm interested. What should I start with? First number to write. 4. Next number. Next number. Next number. Next number. Next number. Okay, I'll accept a point. Let's put a point. This is now your paycheck, which actually doesn't look too bad. Okay, 40,630. But wasn't it supposed to be 406 million? Did we lose some meaning? A little bit of meaning lost in that by putting the decimal point there. Taxes. Okay, so what do we do to make sure we got 5 sig figs? To get those 5 significant digits, we have to have scientific notation. We have no other choice. Until we use scientific notation, those zeros are questionable. Okay? Technically, they are not significant. We can't even reference them as being significant digits. I have to use scientific notation to get this into the proper terminology, because this has now lost a significant portion of your paycheck. And we would then go through and use 4.0630 times 10 to the 8th. Meters, you get paid in meters. Why not? Yes?
Why'd you go to 5 sig figs?
Because initially I'd asked for 5 sig figs. I just said put it in 5. Yeah, it's arbitrary. Next question, what happens if I report it as, stupid eraser, 40.630? It would now be 10 to the 7th. Is everyone okay with that? We counted for one spot, we can get rid of it in the other spot. Am I in scientific notation?
No.
According to the strictest definition, no. You are no longer in scientific notation. Don't get me started on whether or not that is a correct statement to make or not. Okay? But according to our scientific notation rules, we have a number in the ones place followed by a decimal point followed by the rest of our significant digits. Our number is in the tens place. That is now no longer scientific notation. Don't shoot the messenger. I think it's dumb too. But if you're asked for scientific notation, you can only have a number in the ones place followed by your decimal, followed by the rest of the significant digits. What if I had instead written... Did it just disappear on me? No. Okay. Now what happens to the power of 10? It's going to have to go up to the 9th. Good. Because we took rid of one of our decimal points, so we have to replace it in our power of 10. Am I now in scientific notation? Again, no. I do have something in the ones place, but the ones place is not a significant digit at this point. I must start my scientific notation with a significant digit. This 0 is not significant because there's a decimal point, which means I have to have a significant digit in front of it. And I do not, so the 0 is not significant. You okay with all that? Okay, I'm pretty sure the next slide just went through that a whole bunch. Okay, so yeah, a whole bunch of that. So here we go. Oh, that was fun. Look at that. We are now done with the PSS chapter, and we're moving into chapter 2, which is now looking at the metric system, and ultimately we're going to be looking at our conversions. We've already kind of ranted, or I ranted about some of this, that our measurement systems are completely arbitrary. We sat down, we said, this is what I want to call a foot, so it is now a foot. And the next person to come up and say that a foot was not a foot either beat up the original person until they started agreeing with him or were killed by the original. Okay? That is how our system comes about, just like politics. Everything else, unfortunately. Okay? So that's kind of how our system is developed. Don't try and say, oh, this is an absolute scale. It's not really an absolute scale. Someone just said this is what we are absolutely agreed to do. Okay? So it's not really absolute. Within those, we have basic units. Okay? The basic units, you'll notice that for some of these, they've been starred, and not for the reason that I was about to say. They starred some of them because we have this English versus American spelling on those. Don't stress on that. There's another big reason why some of these get starred. And in fact, it's actually better to star gram more than any of the others. It's a bit weird. Why would we star gram?
Isn't a gram like super tiny? Like relative to most?
Some of those other distances, yeah. If we look at length, a meter's a pretty sizable length. Volume, liters are pretty sizable. Seconds is kind of small. But gram, in kind of comparison to the mass of all things we've got to measure versus, say, the volume or length, all those other things, a gram does seem kind of small. Okay? And that's partly what's going on with why a gram is weird. Did anybody go back and watch that video? I said we should watch that because it was kind of neat. Yeah. Kind of I could show it now, but it's freaking 10 minutes long. I don't want to deal with it. The video is all about talking about a sphere, the most perfect sphere made by man. Okay? It is a sphere of silicon atoms, a single crystal of silicon atoms, which is incredibly impressive, though when you look at it, you're just like it's a shiny marble. Okay? It's incredibly impressive to make a single crystal of any element, because as soon as you bring things together, are they going to pack perfectly? No, there'll be a little bit of a wiggle in it, and they'll shift off of each other. It's now no longer perfect. So to create a single crystal, we have a perfect crystal of silicon, which is defined as, in their case, a kilogram, which is the base unit for mass. It's kind of an odd statement. The kilogram already has some kind of weird prefix associated with it. A gram does not have a weird prefix associated with it. Why? Because they defined the kilogram first, okay, with a different name. I think, according to the video, I think it was a grav. Okay, and then someone came through and said, well, most of the stuff I measure is smaller than a grav. Okay, that person would likely have been a chemist saying, I'm going to do things at a smaller scale. Because if I start playing with uranium on the kilogram scale, it becomes very dangerous. Play with it on a gram scale, it's not quite as bad. Okay? So the size constrictions of what we're working with kind of changed. So they shrunk it down to a gram. And so, well, how can we relate the gram back to the grav? Well, they defined a gram to be 1,000th of a grav. Once they defined that, they then back calculated and said, okay, well, a grav will change the unit to become 1,000 grams. And what's our prefix for 1,000? Kilo. There's our kilogram. Okay? So the kilogram was our initial statement for mass. We then kind of shifted our perspective on it and then had to kind of back calculate what was going on with it. Okay? For that reason, when we talk about base units, the official base unit for mass is the kilogram. That is what we measure everything off of. Okay? However, what is most useful for us when I'm talking about a base unit, okay, I'm referring to a gram. And I'm going to attempt this semester to no longer refer to it as the base units, but as the core unit. Okay? Core meaning that when I go through to change the size, instead of looking at meters, I want to look at a really large distance. I'm going to take my core unit for length, and I'm going to append a prefix to it to make it a larger value. So in this case, I could make it kilometers. Okay? So we'll look at our core units versus our base units. The core units we'll try and reference as our meter, grams, liters, and seconds. We will vary off of that by using Greek prefixes. The symbols associated with those core units are shown to the right. Why do we use shortened symbols? Yeah, there was the nice answer, and the nicer answer, and then the sarcastic correct answer. Okay, it's faster to write single symbols, and we're inherently lazy. We don't want to have to write everything out. Okay. So when we go through to look at our units, particularly the metric system, we can now scale off of our core unit to either larger, much larger values or much smaller values by appending a prefix to it. That prefix implies a power of 10. Okay, some numerical value of a power of 10. Those with the King Henry thing, was it king for kilo? Oh, it's not even up there. Henry is Hector, right? Okay. The King Henry thing kind of attempts to put some mnemonic device behind all of these symbols so that you can then attach numerical values to them. If you want to use that, it's not a good idea. And the shifting of the decimal places is also a questionable idea. What I would recommend you do with all of your conversions is follow your units and memorize the symbols tied to them. For instance, if I ask you centimeters, what you should be telling me is that a centimeter is 10 to the negative second meters. The centi just meant 10 to the negative second. If I'm looking at centimeters, then it implies 10 to the negative second meters. Okay. Use the Greek prefix and equate it directly to the power of 10. When we go through and work with our conversions, that helps solidify and ensure that you get the correct answer all the way through your conversions. If instead you memorize that the relationship between centimeters and meters is 2 decimal places is one option. Which way would you shift the decimal? Well, that's a good question. The other option, how many centimeters are in a meter? There's the number, 100 meters, or 100 centimeters are in a meter. The issue with that is that 100 is not 10 to the negative 2. Okay. There are some cases where the power of 10 ends up swapping where it manipulates if you go based off of your standard memorizations for what those values mean. If you instead memorize the table, the power of 10 always affects the base unit. So let's take a look at, almost. You notice as we cheat and looked at those red boxes, that's a lot of stuff to have to go through and memorize. We already told you to memorize 36 elements, which sounded like most of the class did. Good job. Okay. Now I'm telling you to memorize a whole bunch of numbers and letters, exponents, and all that other nonsense. That can be a lot of work. So what I will do is now tell you a kind of shortcut on this. That shortcut is we very rarely will ever look at Terra anything. Why not? It is way too big for us to ever deal with in the lab. So what we're going to be primarily concerned about are units that we will work with in the lab. The most common ones we'll encounter will be kilo, centi, and milli. You need to know those three like the back of your hand, like you already have done with the elements that you bothered to memorize. Okay? So kilo is a lowercase k, and it means 10 to the third. Centi, lowercase c, 10 to the minus 2. Milli, lowercase m, 10 to the negative 3. Those 3 units you need to know, okay, or Greek prefixes. The rest of them, if you see them, say, on a test, don't flip out entirely. Look to the front of the test. More than likely, I'll tell you what it means. Okay? Or look carefully within the question. The question probably tells you what it means. Okay? If you see it in the homework, I do not expect you to have it memorized, and neither does the textbook. What does the textbook and myself expect you to be able to do? There's a chart in your textbook. In fact, it looks an awful lot like this because I stole it from the textbook. use the chart. Okay, so let's take a look at that first one. What we want to do is try and convert this across with our number and our new unit. So the very first step is to convert our number into scientific notation. Scientific notation meant number in our ones place, decimal point, rest of our significant digits. How many significant digits in that first number? 2 sig figs, which means when I go to scientific notation, I will end up with 1.2 times 10 to the, was it third? Oh wow, it was. Third, and you'd be wrong. Meters. Okay. I want now a number and a new unit. Okay, well, my new unit is right here. What did 10 to the third mean? Kilo. So my number becomes 1.2. I had nothing to the number. And now, kilo with a lowercase k, kilometers. And I now have my new unit, new everything set up already for me. Crank through the other ones. You got questions? So, then our numbers, 1.2 all the way through. Oops, sorry. Look at that. Numbers came out the same all the way through. The only thing that's really changing is where we're shifting that decimal point and trying to come up with some interpretation with it. So if we move to the second one, 1.2 times 10 to the, we went 1, 2 places. So 2 shift, and it needs to be negative 2 because I'm looking at a small number, not a large number. Okay? And I'd still be wrong. Seconds or S, I'll accept both. My new unit needs to become centiseconds.
Yeah.
It's true.
Questionable.
No, it's valid.
Just because we never hear.
Okay. How often do we use centiseconds? Not very often, which is why you haven't heard it. Okay. How about the next one? 10 to the negative second liters, and we end up with centiliters. Okay. Last one. How far did we shift our decimal? 1, 2, 3 to get it into scientific notation. So we've got a 3 shift. We're looking at a big number or a small number? Small number, so it needs to be a negative. Unit was grams. My new unit becomes milligrams. Okay? Questions on that? Okay. So the next part we want to kind of set up is looking at what we can do with this new fancy notation. Okay? So we want to kind of address fractions, and fractions are everybody's favorite thing to look at. Are we done? I was looking at the clock. 2:15. Okay, yeah, we still got half an hour. Okay. So, the English, everybody should be relatively familiar with. There are 1,000 meters in 1 kilometer, which we could then switch to mathematics. 1 kilometer equals 1 km, or 1,000 meters. Those on their own are kind of defined units. We can't do anything per se with those. So what we want to do is somehow convert that into a fraction. How could I convert that into a fraction? And I'm going to end up with the statement 1,000 meters over 1 kilometer. What does this equal? 1. Which means if I try to use a conversion factor, I can use this as a way to convert between units, meters and kilometers. Because all I'm doing, if I multiplied by this value, would be multiplying by 1. Doesn't change the numerical value. Why would I ever multiply something by 1? That doesn't make any sense. I'm going to get the exact same value. Except now I can change my units by multiplying by 1. So it can allow me to simplify and adjust things by setting it up in this fractional notation. Did I have to solve for it in this fashion? What was an equally valid fashion to organize that? Wrong. 1 kilometer over 1,000 meters. Equivalent. Still 1. And this, depending on what I'm trying to do, will allow me to play around with my units. Which means whenever we encounter an equality, we can set it up as a fraction, and it probably makes sense to immediately write it into that fractional state. Because as we'll find, when we go through to do our conversions, we will be using fractions, numerator and denominator. The sooner you can accept and use that method, the better off you'll be. Okay? Our numerator, when we refer to it, will always be on top. Our denominator will always be on the bottom. We can swap these backwards and forwards. It is this conversion setup or our conversion factor that allows us to go through and solve things. So when someone says, oh, I can't solve this problem because I don't know what to do, well, as soon as we put it into this format, like, oh, well, that's easy, I can solve it. Okay? English is saying the exact same thing. When you're saying you cannot solve a word problem, you are not saying you can't solve math. You are not saying you can't solve chemistry. Believe it or not, who you should be blaming for your lack of understanding or your lack of ability to solve that question is completely counter, and nobody ever does it. You should be blaming the English majors. They're the ones screwing you over. When it deals with math and our conversions, they're already set up. The issue is that we are now trying to take that information and put it into a language that has already been so confused and befuddled that it now becomes confusing. Okay? Take it out of the English, into the mathematics, into the conversion, and you're set. Break it into each of those steps. Okay? So we can do the same thing with centimeters. 1 centimeter over 10 to the minus 2 meters. Why is this helpful for us? Well, let's go back to what centi meant. What did centi mean? Centi meant 10 to the negative 2. What do I have? 1. Everything canceled out. Okay. What if you're like, well, but I can't remember where to place the power of 10? Okay, well, let's say you messed that up. You did this. Is there a quick way that we could potentially check that? What does centi mean? 10 to the negative 2. So that C meant 10 to the negative 2. Is that equal to 1? No. You put the power of 10 in the wrong spot. Notice that when we go through to do these conversions, you will find that your power of 10 should always go in front of. Remember, we didn't like base as a term. We changed it. Our core unit. Our core unit, in this case, is meters. So if we're trying to figure out a conversion that allows me to convert between centimeters and meters, and I don't know what numbers to put in there, okay, but I do remember that centi meant 10 to the negative 2. Okay? In this conversion, the power of 10 always goes in front of the core unit. Which is the core unit, centimeters or meters? Meters, which means the power of 10 goes kind of except on the bottom. We can get a little bit better than that. In front of meters. There's now no confusion about it because you know the power of 10 always belongs with the base unit. It never goes with your prefixed unit. Okay? Those of you that have done conversions the old math way will find that there are some cases where you're like, but that doesn't work. That's because the math way didn't define a set of rules for what the prefixes meant. They went through and did it based off of what they remembered to do calculations quicker and easier. Okay? Your power of 10 will always go in front of the core unit. Some mathematical manipulations. Those of you that don't like exponents or negative numbers can feel free to close your eyes, shut your ears, do whatever, fast forward the video. Okay? What does a negative number actually mean? What was that? A negative number doesn't mean positive. Opposite of positive. Okay. But you may be, well, that's kind of silly and dumb. 10 to the positive 2 is 100. Where do the 10s go? In the numerator, because that's where they're located, right? Where's the 10 in 10 to the negative 2? Where's the 10 written? Right there. In the numerator or denominator? Maybe it'll help if we put in a denominator there. It's in the numerator. What does that negative mean? Do the calculation of 10 to the second in the opposite location. Where is the 10 to the second right now? In the numerator, which means I should do the calculation all the negative means is opposite of whatever the positive is. Okay? Mind-blowingly weird and simple all at the same time, and yet it screws with your ability to process everything. Okay? Negative signs you will learn to be your enemy. Okay? And everything we do in science is to try to mitigate and prevent those negative signs from showing up because it's confusing. Okay? You don't like dealing with what the negative means? We've got this fancy-dancy little thing called a calculator. You can punch in the buttons and it spits out an answer. That works lovely. Okay? But there are shortcuts if you understand what it means. 10 to the negative 2 means I do the calculation in the denominator. There it is. What if I have this? My calculation is 10 times 10. But I need to do it in the opposite location of where I am. Where am I right now? In the denominator, which means there's my answer. Okay? Neat little feature of fractions and negative signs, just so you're aware. Okay? Which kind of brings up the issue that some people have memorized, particularly when it comes to kilo, centi, and milli for their conversions. I told you the power of 10 always goes in front of the core unit. So we end up with 10 to the negative 2 meters is 1 centimeter. That value involves a negative and an exponent. We tend to freak out at those. The other way that people memorize that value is instead of 10 to the negative 2 meters is 1 centimeter, they memorize it as the exact same thing, except now what I've written doesn't have a negative value, doesn't have exponents, and now I feel more safe and comfortable in my life. Unfortunately, your power of 10 is now affecting your complex unit, the prefixed unit. Okay? We might say, well, okay, then we'll just make sure the prefix unit always has the power of 10. Try it with kilo. Doesn't work. Okay? Always put your power of 10 in front of the base unit. Memorize the standard exponential values that we told you. You don't have to worry about this. So if somebody tells you a kilometer is 1,000 meters, you say, no, 10 to the negative third meters is 1, or 10 to the third meters is a kilometer. Okay? It's a bigger mouthful, but it gets you the correct memorization when writing it down. Okay? So which do you want to be able to do? say these things easier or get the answer correct when you take a test?
Correct on the test.
Right on the test is probably what you want. Okay? The power of 10 in front of the base unit will get you the correct answer when you write it down. Converting them into the hundreds or thousands or whatever you want to do in that case will make it easier to say the conversion. It screws up your calculation. Okay? So, another mathematical test. What's the answer to that first one? 3. How'd you do that?
3 times 1.
You said 6 divided by 6 is 1. So the next one. 3 and 3 is 12. Next one. Come on, work with me here. 4, and we get 3/4. Why bring up this point?
Easy.
I mean, it doesn't have to make sense, but we can cancel our units just as easily as we can cancel numbers. Okay? We will be canceling units as we move through the semester. The units solve the answer for you. So follow your units, set up your conversions, and everything runs beautifully. Okay? So, this is a bit of a challenge here. Okay? So you might want to take a second, breathe in deep. Don't all breathe in deep at once. Let it out. We're going to start with a very difficult calculation. Do not shout out the answer if you're that good at the calculation. Take a second, figure it out, write down your answer. Are we good? What's the answer? 36 feet. Inches. One of the above. This is why I write things down. How many of you actually wrote anything down to do that calculation? Nobody? Nobody wrote anything down. Did it in your head. Okay? Fair enough. Chapter 2, all of the conversions you will do, you can do in your head. And what the bad students will do is do it in their head. And then when we move to the section where we talk about units that you have no conceptual understanding of, you will then blame me because I didn't explain to you how to set up the conversions properly. And that's really just because you didn't write it down. So, write it down. How do you do this conversion? And make sure that when you go through and do the calculation that you get the correct answer, both numerically and units. Those of you not writing have a problem. How do you calculate this? Okay? I don't see 36 anywhere in there, so I've already got a problem with that. Okay. 12 inches over 1 foot times it by 3. So now I look at it and I get 36, but I get 36 inch feet over foots.
Over 1 inch.
No, just over 1.
No, I'm sorry, 3 feet over 1. I don't know.
X over 3 feet.
All it is a plural. What happens with our feet and foots? The units cancel and we'd be left with 36 inches. There was another suggestion that I heard a couple people shouting out. What was that suggestion? I'm going to start to guess at it because I'm not very good at it. 12 inches over 1 foot equaled X inches over 3 feet or 3 foot.
No, switch it.
Feet goes on top.
No, that's right. Solve for X.
Cross multiply.
Cross multiply, and what do you end up with? The exact same thing up there. Okay. Both of these methods are equally valid at solving this question. It allows you to do a single conversion. The bottom, or the second method, is not very good at solving multiple conversions because you now need to set up multiple equalities to go through and do each of those conversions. If you have to string together 3, 4, 5 conversions, you're filling up half a page worth of calculations. If you instead use the upper version, you can string together 3, 4, 5, 6, an infinite amount of conversions in a single line that does it all as one kind of fell swoop or one step. Okay. Most people do not like doing the red format. And that is because most people have not had to deal with chemistry where you are doing multiple conversions in a single question. Why go through and look at either of these situations? Why do I care how you solve a problem? Can you do this conversion in your head? Yes. What if I ask the question, how many of you can do that conversion in your head? Why not? You don't know the conversion factors. Okay. Even if I gave you those conversion factors, you would probably still not be able to do it in your head because it is now a system or outside of your realm of comprehension because you haven't been doing it for 16 to 20, 30, 40 years, however old you are. The conversion of inches into feet you've been doing for a long time. You've internalized that calculation. Do not internalize anymore. Okay? You must write it down. The whole point of chapter 2 is the notation. We will do conversions backwards and forwards, and you'll be like, this is dumb to show this work. You're right, it is dumb. I will freely admit it. Okay? But what we are giving you the opportunity to do is to test a question that you already know the answer to. You are building the notation, the formalized idea of how to solve a problem. You can then check that internally in your brain because it's an easy question. The instant we change those units, you can no longer internalize the calculation, which means you have to rely on the notation, the formalism used to solve the question. That formalism is dimensional analysis. And that is what we are doing in the red box. It is also what we're doing in the purple section. The purple section only does it one step at a time. Okay. That reference, we skipped through all of that, is your unit. Your textbook likes to call it the unit analysis method. What we want to go through and do is set up individual steps that allow us to approach and solve every single question. Those of you in physics, how many equations are there? Anybody taking physics? Let's try that. Okay, we got a couple hands. Do you guys have equations to memorize in physics? Mm-hmm. There are no equations in physics. It's units. All it is a unit conversion. You're changing from one unit to the next. There are no equations. Why do we have you memorize equations in physics? It's easier for us as teachers. Most chemistry classes will have you memorize loads of equations for how to calculate one thing to another to another. Why? It's easier. Not only is it easier, what's the first thing you ask for? What's the equation? There is no equation. It's units. Track the units. Step number 1, know where you're aiming. Write down the unit for your answer. Step number 2. Find something that has that unit in it and start working with it. That is your given value. Step number 3, mess with your given values units until you get the correct answer. By messing with, we need to insert conversion factors as necessary to go through and solve it. So if we look at this simple question that we just went through and did, inches in feet. Step 1 is, what unit do we want for a final answer? What information are we given? Okay. In this case, we're only told 3 feet. Which I'm going to write as foot just because it was obnoxious for me to do that last time. Are foot the same as inches? No. Okay, so we don't have our answer. This is a good question to ask. If you go through and you find out that inches and inches, you should stop working and just write down the number. Okay? Some kind of jerk teacher might give you a whole list of numbers and make you think you got to do some crazy conversion when I actually gave you the answer. I mean, that weird person gave you the answer. Okay? So foot and inches are not the same. What has to happen? What has to happen in this next line? What do I want to happen? I want a little bit more detail than in conversion factor.
How many inches are in a foot?
I would step back from going all the way to inches to feet. What unit shows up in my numerator? Inches. Good point. I didn't say answer or question. In my answer, the unit is inches in the numerator. Is inches in my numerator yet? No. So minimally, what has to show up in that random box? I have to have inches, and it had better show up in the numerator. Why the numerator?
Because you need it in the
That's where it is in the answer. Okay. What can I convert inches to? I can convert it to centimeters. You know, why would you ever convert to centimeters, Mike? That was a dumb idea. Okay. Well, maybe I started with centimeters.
So you didn't you started with feet?
What did I start with? Feet. So what do I want to have happen? Feet had better cancel out. For that unit to cancel out, it needs to show up in the opposite location of where it originally is. So it has to be in the bottom. So now the question becomes, do I know the conversion factor between inches and foot? If I know, now I can bring in the numbers. What are those numbers? The 12 belongs where? Ooh, numerator, no. Everybody else was right. In front of inches. What shows up in front of the foot? 1. Now I have my conversion. Okay, you may, this was dumb. Why did you do such a simple example? Because all of them are this dumb. Okay, every single one. Okay, the issue becomes, where do you find that conversion factor? That is it. Okay? So, mass in grams. 325 milligram aspirin tablet. What do I want for my answer? Okay. What information am I given? I'm given milligrams, and officially 325 milligrams. Step 2. Okay. Let's focus on what we would ideally have showing up. What would I ideally see in this next step?
Grams on the top.
Why?
That's what you're trying to get to.
Grams need to show up in the numerator because when I look at my answer, grams is in the numerator. It's as simple as that. What ideally do I want in the denominator? Milligrams, because I'm trying to get that unit to cancel. Do I know a conversion between grams and milligrams? Said another way, did Mike tell me earlier this very same day that you should know a conversion factor between milligrams and grams?
Yes.
-3.
Okay. We said that milli meant 10 to the negative 3. 10 to the negative 3 needs to show up in front of
The core.
the core unit, which in this case is grams. What shows up in front of the milli? 1. What are my units?
Grams.
Grams. All I got to do, punch it in the calculator, I'm done. Okay, if I punch it in the calculator, we'll take 325 times 10 to the minus 3. So we're multiplying everything in the numerator. Then we'll take everything in the denominator, multiply everything in the denominator. What's in the denominator? 1 and
milligrams,
1. 1 times 1.
1.
Okay. So all I got to do is multiply the top out, and I've got my final answer. Boring. Is that what you said? I agree.
I said 20.
I don't even know what the number is. What is it? Calculator spits out, should spit out 0.325 grams. Like, oh, I could have just done that stupid King Henry thing. Yeah, you could have. You'd probably screw it up. And you would screw it up once, and that one time you would screw it up would be during the exam. So don't do that nonsense. Do it this way. How about this next one? What do we want for an answer? Micrograms. Ooh, that's nasty. What does microgram look like? Oh, I don't know. I wish somebody
You didn't tell us that one.
would have given me that information. I didn't really give it to
say
you.
we're gonna use it.
He said if you were to use it, you put it.
I said if you were going to use it. Micro
-6.
is 10 to the negative 6. What information am I given to start with? Milligram. I like the units forward answer first, followed by our 325 milligram in front. We now go through and look at our calculations. Sorry, that's a bad color. Ideally, what do we want to happen in our very next step? We want micrograms, and what do we want on the bottom? Milligram. Is there a conversion factor written anywhere not by you that relates microgram to milligram? I'm going to take that silence to mean no, we don't have that conversion factor, so we got to convert something else out. So what do we want to deal with? We want to deal with the microgram or the milligram? Okay. Milligram probably makes sense because we don't know what's going on with that microgram yet. So we want to convert that milligram to something else. I can convert milligrams into grams. And I can do that because I did it earlier. That's one dodge, nice answer. Milli means 10 to the minus 3. Goes in front of my core unit, which is grams. 1 goes on the bottom. I now go through and look at my conversion. Do I have my answer yet? Let's try that. No, I've got grams and I want micrograms. What needs to show up in my next conversion? Grams needs to show up in the denominator, so the unit cancels. What needs to show up in the numerator? Micrograms. Do I have a conversion factor that relates micrograms to grams? Yes. Micro represents 10 to the negative 6. The power of 10 shows up. Does not show up in the denominator. In front of our core unit, which happens to be in the denominator. What unit do I now have? Micrograms. What answer did I want? Guess what I can do? Punch it into the calculator and I'm now done. Yes?
Why'd you put milligrams on top? Is it kind of negative too? Just don't want you like on the opposite of each other.
The power of 10 will always go in front of the core unit. Which is the core unit, grams or milligrams?
Grams.
Grams. So the 10 to the negative 3 needs to go in front of grams.
Before you did the grams, wasn't it the micrograms and the?
So we had micrograms initially at first. Do you know the conversion factor between micrograms and milligrams?
No.
No. So we need a different conversion. Do you know how to convert milligrams to anything else? Grams. There's our new conversion. Why did I do 10 to the negative 3 grams over 1 milligram as opposed to 1 milligram over 10 to the negative 3 grams, which is what I think you're asking about? 325 milligrams. The milligram unit shows up where? In the numerator. Does that show up in my final answer? Micrograms does, but does milligram? No. So what do I have to do? What do I have to do to the milligram unit? Sort of. by canceling it from the system. To cancel the milligram unit, where does it need to show up? Here, it's already in the numerator.
That's what I was asking, because there's in the middle, like, there's in the, so why, okay, I think I get it.
If you put the milligram up here, you can't cancel the unit.
Yeah.
Numerator, denominator to cancel. Does it make a little more sense? Maybe. And we will have to stop there, unfortunately, because we're done.